In this video, we will learn how to solve a statically indeterminate member which is subjected to axial load. But before that, we will have some introduction of the principle of superposition. The principle of superposition is used to determine the stress or displacement at a point in a member when the member is subjected to a complicated loading. For example, if we consider this beam is subjected to a point load, a moment, and a UDL. So this we can consider as a complicated or complex loading. So these types of problems can be made easy by using or solving by principle of superposition. So in principle of superposition, we subdivide the loading into its components. The resultant stress or displacement at the point can be determined by algebraically summing the stress or displacement caused by each load component applied separately to the member. So if we consider this beam which is subjected to these three different loadings, and if we want to find out the support reactions at A and B, we can simply divide the loading into three parts. First, on the same beam, we will apply this point load and we will find out the support reactions. Then we will apply this moment which is acting at center, and again we will find out the support reactions. So these are RA2 and RB2. And finally, we will apply the third loading which is UDL over this beam alone, and then we will find out the support reactions. And then using the law of superposition, the support reaction at A is a combination or summation of these individual support reactions due to these separate loadings. Similar for NB, we can find out the support reactions in a similar way. Similarly, we can find the deflections, a shear force, or bending moment at any location in this beam by using this concept of law of superposition. To apply this law of superposition, we must fulfill the two conditions. The first is that the loading must be linearly related to the stress or displacement that is to be determined. It means that the Hooke's law should be valid. The stress is directly proportional to strain. The second condition to be fulfilled is that the loading must not significantly change the original geometry or configuration of the member. It means that if we consider this diagram, here a point load is acting at the end of this cantilever beam and it is producing this much deformation. We can divide it by using the law of superposition, this load P into P1 and P2, and we can separately apply this loading P1 and P2 to the same structure, and we can find out the resulting moment or deflection due to these individual moments. But if this P loading or it is producing too much deformation, in this case this D distance, so here if we find the moment at this fixed support which is equal to P into D distance, but if this deformation is too large, then this D distance will not be equal to this distance which is D1 or D2. So in this case the resulting moment may not be equal to the moments produced by this loading which is P1 into D1 or P2 by D2, because this D distance is not now equal to D1 and D2. You can also understand it. For example, this beam is fixed here, and if you bend it too much or if this deformation is too large, it will rotate about this point. So as a result, this D distance will be smaller. So law of superposition is applicable to very small deformations which can be neglected. Next thing is the statically indeterminate axially loaded member. So here we have a bar AB which is fixed at both ends A and B. So this type of problem is a statically indeterminate problem because in this situation the number of unknowns to be determined are greater than the equations of equilibrium to solve it. So consider the bar shown which is fixed, supported at both of its ends. From the free body diagram, the equilibrium requires that if we take the summation of vertical forces, this is a free body diagram of the same structure. So we have fixed end here, we have a vertical reaction here, and we have a fixed end B, we also have a vertical reaction here. So here it is FA, here it is FB. If we take the summation of vertical forces, so it says that FB plus FA minus P, because minus P is here, P is acting in downward direction, so according to the considered positive direction, so P is acting downward. So here the negative sign shows that it is acting in the downward direction. So this is the equilibrium equation for this structure. Here we have only one equation, but we have two unknowns to be determined, FB and FA. So from one equation we cannot find two unknowns, so we need two equations to find the two unknowns simultaneously. So we need at the same time another equation so that we will develop. So this type of problem is called statically indeterminate case or statically indeterminate structure. To establish an additional equation needed for the solution, it is necessary to consider how points on the bar displace. For example, if we look on this free body diagram, the end A is fixed and B is fixed. So end A cannot move or displace with respect to end B. Or we can also say that end B cannot be displaced with respect to end A. So by using this, we can develop a compatibility equation. An equation that specifies the conditions for displacement is referred to as a compatibility or kinematic condition. So in this case, the displacement of one end of the bar with respect to the other end should be equal to 0. The displacement of end B with respect to end A, or the displacement of end A with respect to end B, should be 0 since the end supports are fixed. So hence the compatibility condition becomes that the deformation or displacement of end A with respect to B is equal to 0. So this equation can be expressed in terms of the applied loads by using a load-displacement relationship which depends on the material behavior. So in the previous lectures we have determined that the axial deformation of a member which is subjected to axial loading can be determined using this expression, which is delta is equal to PL over AE. Here P is the applied load, L is the length of the member, A is the cross-sectional area, and E is the modulus of elasticity. So if we look at this free body diagram of this structure, so from A to C, over this segment of this bar AB, we have axial tension. If we cut a section at this location, at this location, at this location, at any location between point A and C, the force will be same, and that is a tensile force, and that is equal to Fa. In this segment CB, so we have a vertical reaction at B and we have a downward force acting at P. So this force is trying to compress this portion of this bar AB. So as a result, this portion will be subjected to compression. The internal force in segment AC is plus Fa, which is tension, and in segment CB, the internal force is minus Fb. So minus indicates that it is a compression. So here we can see the skirt section in this portion and in this portion. So if we apply this displacement equation to this segment and this segment, so we have this form. It means that the summation of displacement or deformation in segment AC and in segment CB is equal to 0, but the individual displacement in this segment and in this segment is equal to FA into LAC over AE, and in this segment this equation becomes the force in this segment, which is FB, into length of this segment, which is LCB divided by AE, and their summation must be equal to 0 to satisfy the compatibility equation. So assuming that A is constant, then from the previous equation we can find FA in terms of FB using and then using equilibrium, the equations for the reaction becomes, this was the equation of equilibrium, we previously write it, and now if we put FA here, we can find out the expression for FB2. So that is the result for the resulting expression for the end support reactions at A and B. So this is the force at end A and this is the force at B. So if we know this applied load, the length of the segments and the total length of the bar, so we can find out the two support reactions. Since both of these results are positive, the direction of the reactions is shown correctly on the free body diagram. So it means that the FA is acting away from the section in upward direction and FB is acting towards the cross section. Okay. These are the important points related to the law of superposition and a statically indeterminate problem. And that is the procedure for analysis. So first we have to write the equilibrium equations, then we have to write the compatibility conditions, and then using a load displacement relationship like delta is equal to PL over AE, we can relate the unknown displacement to the reactions, and then finally using the equations of equilibrium and compatibility equations we can find out the unknown reactions or forces. Here in this diagram, most concrete columns are reinforced with steel rods, and since these two materials work together in supporting the applied load, the forces in each material become statically indeterminate. For example, this is a concrete column that is subjected to external loading. So that external loading is resisted by concrete as well as steel. So the same loading is resisted by concrete and steel, but with different proportions, so that makes it indeterminate. Now we will solve an example. This is example 4.5. The steel rod shown in figure has a diameter of 10 mm. The diameter of this rod is 10 mm. It is fixed to the wall at A, and before it is loaded there is a gap of 0.2 mm between the wall at B prime and the rod. So this rod is fixed at end A, but on the other wall there is a gap between the end of the rod B and the wall B prime. The gap is 0.2 mm. Determine the reactions at A and B prime if the rod is subjected to an axial force of P equal to 20 kN as shown. So at this collar at point C, a force of 20 kN is acting towards right. So we have to find out the reactions at A and the reaction at B prime. Neglect the size of the collar at C. Take modulus of elasticity for steel 200 gigapascals. First of all, we will write the equilibrium equation. As shown on the free body diagram, we will assume that the force P is large enough to cause the rods NB to contact the wall at B prime. The problem is statically indeterminate since there are two unknowns and only one equation of equilibrium is available. So this force causes this and B to displace towards right. So it can only move by 0.2 millimeter here to fill the gap. But after 0.2 millimeter displacement, there is a wall and this end will come in contact with this wall and it will not further allow it to displace towards right. In other words, it will provide a reaction in this direction to resist the displacement of this end. So if we look here at the free body diagram of this rod, and applying the equation of equilibrium and considering the right direction positive, the equation of equilibrium becomes minus Fa minus Fb plus 20 10 raised to power 3 newtons. So we have converted kilonewton into newton by multiplying with 10 raised to power 3. So this is our equilibrium equation for this case. Next, we will write the compatibility equation. So the compatibility requires that the displacement of NB with respect to NA can be only 0.2 millimeter. Furthermore, it cannot be displaced. So the force P causes point B to move to B prime with no further displacement. Therefore, the compatibility condition for the rod is that the displacement of NB with respect to NA is equal to 0.2 millimeter, or in units of meter it is 0.0002 meter. So this portion of the rod is subjected to tensile forces and this portion of the rod is subjected to compressive forces. So now we can find out this displacement, which is equal to the displacement in this portion plus displacement in this portion. So delta for this segment plus delta of this segment should be equal to 0.0002 meter. So this displacement can be expressed in terms of the unknown reaction using the load displacement relationship applied to segment AC and CB. So working in units of newtons and meters, we have this. So that is the displacement of NB with respect to A, which is 0.0002 meter, and that is equal to PL over AE for segment AC minus PL over AE for segment CB. Because segment AC is tension, it is positive. Segment CB is in compression, so we have put a negative sign here. And the P has been replaced by FA, which is a force in segment AC, and FB is replacing P because it is a force in segment CB. Now put the values for length in meters, the cross-sectional area of the rod, and modulus of elasticity in both these expressions, and solving it we get this equation. So this becomes the second equation which is obtained from the compatibility condition. And now we have two equations, one from the equilibrium and the other is from the compatibility condition. So solving FA and FB simultaneously using equation 1 and 2, we get the result FA is 16 kilonewton and FB is 4.05 kilonewton. Since the answers for FB is positive, indeed NB contacts the wall at B prime as originally assumed. In other words, the directions of FA and FB assumed are correct. Now let's move to the second example. Here, the aluminum post shown in figure is reinforced with a brass core. So this is the aluminum post outside and it has a filling of brass core inside. If this assembly supports an axial compressive load of P which is equal to 9 kPa, applied to the rigid cap, determine the average normal stress in the aluminum and the brass. Take modulus of elasticity for aluminum 10 raised to power 10 into 10 raised to power 3 ksi, and for brass it is 15 into 10 raised to power 3 ksi. So here this P load is acting over a rigid cap. So first we will apply the equations of equilibrium. The free body diagram of the post is shown in this figure. Here the resultant axial force at the base is represented by the unknown components carried by the aluminum, which is FAL, and brass, FBR. The problem is statically indeterminate. Why? Here this post is fixed at the bottom, but it is free at the top. So it is not indeterminate because of extra support reactions. It is indeterminate because this load, which is P, which is equal to 9 kb, is resisted by two materials. One is aluminum and the other is brass. So we have to find out what portion of this load is resisted by aluminum and what portion of this load is resisted by the brass in terms of stress. So first we will write the equilibrium equation. So we will apply the equilibrium equation in vertical direction and considering upper direction positive. So it is minus 9 kb because the applied load is acting in downward direction, plus FAL, which is the force in aluminum, plus the force in brass. It is denoted by FBR. So that can be shown here. This is the applied load which is acting in downward direction, but the overall reaction at the base of this post is FAL plus FBR. So we have to find out how much is FAL and how much is FBR. So here the compatibility equation states that the rigid cap at the top of the post causes both the aluminum and brass to displace the same amount. So here we will use the compatibility condition that this applied force causes both aluminum and inside brass tube to displace by the same amount. It can be written as like this one: delta AL is equal to delta BR, or the displacement in aluminum is equal to the displacement in brass. So we can show using the expression we derived in previous slides the displacement for aluminum and the displacement for bar, like this one. So this is the displacement in aluminum and this is the displacement, a downward displacement in the brass. It is FAL over AE. This is FBR into L over AE for brass. We can simplify. We can write this equation in terms of the force in aluminum, in terms of the force in brass. So now put the values for area of aluminum, area of brass segment. Similarly, the modulus of elasticity for aluminum and modulus of elasticity for brass. And then simplifying and solving it, we get this equation that the force in aluminum is equal to 2 times the force in brass. So this is the compatibility equation, or the second equation we need. Now using the first equation, which is the equation of equilibrium, here we have two unknowns, and this is the second equation which is obtained from the compatibility condition. So here we have also two unknowns. So solving them simultaneously, we can find the force in aluminum and the force in the brass, which is 6 and 3 kb respectively. Since the results are positive, indeed the stress will be compressive. The average normal stress in the aluminum and brass is therefore the force in the aluminum divided by the area of the aluminum tube. So force in aluminum is 6 kb and the area of aluminum tube is equal to pi r square. Here it is to be noted that the aluminum tube is hollow from inside. So we will use pi into external r square minus internal r square. So it becomes 0.637 ksi. Similarly, the stress in the brass can be calculated by dividing the force taken by the brass, which is 6 kb, divided by the area of brass, which is pi r square, and it becomes 0.955 ksi. So these results are shown here. Thank you.